Hey there, Braves. Why am I twirling a lightsaber around in my classroom, dressed like a doofus? Well, this week, in astronomy, we're talking about light, and all of the wonderful things that light has taught us about the universe, from galaxies all the way down to single-star systems. So, strap in. You're about to get a lesson from a galaxy far, far away. So this week, our topic in astronomy is light and the light spectrum. Believe it or not, there's a lot of different types of light. There's more than just the visible light that we see. In fact, most of you are probably aware, even if you can't think of it right off the top of your head, of infrared light. This is what all of those night vision goggles and things tend to use, because there's tons of infrared light being emitted by all sorts of different things. In fact, infrared light is just basically heat. And when infrared is released, it's in a spectrum of the light spectrum, the electromagnetic spectrum, that we can't see, even though it's everywhere. It's invisible to us. Well, there's more than just infrared light. In fact, we have things from gamma ray to ultraviolet radiation, the stuff that the sun puts off that gives you a sunburn, all the way down to radio waves. Yes, radio waves and microwaves, the things that our phones and our radios in our car all operate, those are all types of light, or electromagnetic radiation. Okay, pump the brakes, Mr. Clemens. Before you go any further, what is the electromagnetic spectrum? And what is light? Hey, I'm glad you asked that question. Let me tell you all about exactly that. Light is also known as an electromagnetic wave. Electro meaning electricity, and magnet like magnet. We found out that electricity and magnetism are related, and that light is emitted from electrically charged particles. Basically, anything that gives off magnetism or electricity can produce light. Basically, when you look at light, think of it like anything else. Gold or silver or iron or any of the other elements. It's not an element per se, but it is a thing of impossibly small mass. Think about taking a gold coin and cutting it in half until you get all the way down to a single gold atom. Well, you would have just that. You'd just have a single atom of gold, but it doesn't really have any crazy properties. It's not emitting energy or anything like that. However, light, if you were to get that down and cut a beam of light in half and half and half and half until you got to the smallest possible unit of light that you can, you would get down to a single photon, just like a single atom of gold. But the difference between, say, gold and light is that gold is matter, it has mass, whereas this photon is really more energy. It's like a dense packet of energy, and it's impossibly small. Much, 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 much smaller than a single proton that you'll find at the center of any atom. So this is a very impossibly small thing. And it sort of has mass, but it also sort of acts like a wave. So as it moves through space, it goes up and down, just like the waves on a pond or in your favorite beach in your favorite ocean, wherever that might be. Anyways, the point is, light itself has different characteristics based on how much energy it has whenever it leaves its source. The more energetic, the more energy it has, the more crazy energy that it has, the shorter its wavelength, and the higher its frequency. Frequency just means waves per second, so how many waves come by you at a given time. And wavelength is just how long your wave is from crest to crest or trough to trough. Okay? So if I have, say, radio waves, which are the least energetic and least harmful of all the electromagnetic waves, it has a very, very long wavelength. In fact, some radio waves have a wavelength as long as an entire football field. That's long. When you get into microwaves, the things that we use for, say, your new cell phones that are on the LTE band and 5G and all that, or the stuff that you use to cook your food very quickly, heat it back up, those microwaves, their wavelength is much shorter, and they are on the order of several inches wide, right? So we went from football fields down to several inches wide. Those have a lot more energy, but they actually have less energy than the light that you're using right now to see me.
Visible light has more energy than microwaves, which is why you shouldn't necessarily be afraid of 5G or LTE, because literally you're being bombarded with much more energetic light than anything else. Like this, if you're worried about microwaves, this thing right here is a heck of a lot more energetic and would be more capable of doing damage, but neither is likely because this is not damaging radiation at all. So anyways, as you move your way up, you get in from microwaves into infrared light. We can't see that either, but it's there. It's basically heat. Right now I'm emitting all sorts of infrared light because I have a body temperature, and that's a good thing because that means I'm breathing. Then we get into visible light, and that has even smaller wavelengths, and it has much more energy. Then you get into ultraviolet, and this is when you actually get to a level of light energy that can cause you harm. Because when you go outside, you're bombarded by UV rays, UVA and UVB, and you've probably heard all of those things, or at least read them on the bottle of a thing of sunscreen. Point being, that is when you finally get enough energy from these waves to cause you harm. It will actually burn your skin, right? You actually get cooked from the UV radiation from the sun. But you can go even more energetic still. And that's when we get into things like X-rays. X-ray radiation goes right through you. It's very high energy, but once it hits your bones are dense enough that it kicks it back or absorbs it. So that's why X-rays work. The problem with X-rays, though, is if you're exposed to too many of them too often, they can cause damage to your DNA and give you cancer and all sorts of nasty stuff, and that's why you don't play around with X-ray radiation. Now, the most damaging and the most energetic would be gamma rays, and gamma rays are something that the sun does produce, but thankfully we have an atmosphere and an ozone layer that protects us from most of them. X-rays and gamma rays are also being produced by our sun, and in large enough amounts that if we were in space unexposed just to be blasted by the full breath of the sun, it would cause all sorts of different health issues, and frankly you wouldn't want to experience that. By the way, gamma radiation is a radiation that Bruce Banner used to become the Hulk. Now, don't go and, again, hit yourself with gamma radiation, because none of you are going to Hulk out, and most of you would just die a painful death. So don't play around with gamma radiation if you ever get the chance. Chances are you won't, though. So, alright, no superheroes here. That's what light is. That was a long explanation for that. Geez, could he have said that any faster? I don't know. Let's keep going.
Most of your light sources, especially the light sources here in the classroom, emit what is called white light, perfectly white light. And if you run white light through a prism, like the all too famous Dark Side of the Moon, the CD cover, the album cover, with the prism breaking up into that rainbow, right? Well, when you run white light through a prism, it separates out all of the different colors in the rainbow. See, white light is made up of all of the colors in the visible light spectrum. So when you run it through a prism, it separates those colors back out. Well, depending on what you're looking at, maybe it's a star, maybe it's the lamp next to your desk, maybe it's the computer screen that you have. If you run that light through a prism, it will separate out all the different types of colors that are in there. And what you might find is different sources of light have different spectrums that are separated out when they hit a prism. Not every light bulb that you have or light source that you have can be separated out into all of the colors of the rainbow, which is why you get those different colors of light from different light bulbs and light sources. Now, this technique or this concept is used in astronomy to identify all of the different types of stars that we can see in the nighttime sky. And we use that information to determine how hot that star is. For instance, the hotter you are, the shorter your wavelength is going to be of the light you emit, and the closer to violet or blue you are. So we can judge your temperature based on the color you are as a star. The redder you are, the lower your temperature, the less energy that light has as it's being emitted. So what I have here are glass tubes filled with gas. And each one of these tubes has a different element, a different elemental gas inside of it in its pure form. Now, why do we have gas inside of these glass tubes? Well, In front of me here is a spectrum tube power supply. And you can see I have a neon tube right here. So inside of this glass tube is neon gas. And on either end is the power source. What we do is we run electrons through this tube and it excites the gas. And when the gas gets excited, it glows. And every element on the periodic table will glow a different color. So it will have a different wavelength on the electromagnetic spectrum. Using this knowledge, we can use a technique called spectroscopy to identify different elements based on the colors they emit. And we can use that with telescopes to figure out what each star is made of. We can even use this technique to determine what elements are in the atmospheres of planets that are orbiting stars dozens and dozens of light years away. Anytime a planet passes in front of a star, it darkens the star just ever so slightly, and it can change the color of light coming through to the telescope. And that can give us a hint at what may be inside the atmosphere of that planet. So let's go on ahead and go through a few examples. What do these elements look like when we excite them with the energy of electrons? Neon. The noble gas, helium. What every star is made of? Hydrogen. It's kind of a pinkish purple. Xenon. The element you need to live, oxygen. A very important element, nitrogen, which is in all of your amino acids and proteins. It's a nice deep purple color. But as you just saw, we can determine the types of elements that are in each star and even in the atmospheres of different planets based on the light that they emit from the electromagnetic spectrum. So just like neon glows in that beautiful bright pink or purple color, well, if we pick up the same frequency coming from an atmosphere in, say, one of the moons surrounding Jupiter, well, we can assume that there's neon inside of that atmosphere. So it's a very useful technique for trying to discern what all the stuff around us in the universe is made of. The only catch is it has to be emitting light. And 99.9% of all of the mass in the universe happens to be locked up inside of stars. So that makes it really easy to determine what most of the mass is in the universe. However, most of the objects in the universe are not stars, and we have no idea what those things happen to be made of. So there is a big hole in our understanding of, well, space and the universe and all of that, but we know quite a bit from just that little bit, those little tiny pinpricks of light that we see in the nighttime sky. Other things that we are able to learn from light is whether or not something is moving towards us or moving away from us. If an object is moving towards us, the wavelength of light that it is emitting over time will get shorter and shorter. Just kind of like when a car goes by on a highway, you hear the kind of sound. As it goes away from you, the sound gets deeper, but as it comes closer to you, as it's nearing you, it sounds higher pitch. The same thing happens with stars and galaxies as they're moving around in the universe. Their light will get a higher pitch or a shorter wavelength if it's coming towards us. And if it's going away from us, well, it will be redshifted, or the wavelength will get longer. So we can tell the overall motions of different things in the sky simply based on whether or not it's been shifted to the blue and had a shorter wavelength, or been redshifted and is moving away from us. Now, redshift and blue shift is also really useful for understanding a very scary concept. And that is the fact that our universe is constantly expanding. In fact, if we look pretty much in every direction, to the exception of 1 or 2 galaxies, everything, every source of light in the universe is slowly being redshifted away from us. So something that should be emitting a yellow light might be slightly yellow-red if it's really, really far away. And the further things are away from us, the more and more redshifted they are, because it took longer and longer for it to get here, and the universe had more and more time to expand and stretch those wavelengths out. So the furthest we look away from us in the universe, the redder the light is, and the closer we look, the less redshifted it has become. This proves to us that the universe is expanding equally in all directions. Now, the scary part of that is that that universe is going to continue to expand until it basically outworks the forces holding matter itself together, in which case all matter in the universe will eventually be ripped apart until it's nothing more than just little bits of energy. And it's going to be called the Big Rip, and that's how the universe is going to end. But you don't have to worry about that. That's at least 100 billion years in the future. So we'll all be dead by then, and the sun and the earth will no longer have been in existence. So don't worry. It's not going to happen anytime soon. But yes, light itself tells us a whole lot about everything that's going on in the galaxy. Do we know whether or not there's life on another planet? Well, maybe we can find that information if we can get certain gases to show up in those light spectra that we know are associated with life. So using the electromagnetic spectrum is very important, not just to astronomy, but astrobiology. It's important to our search for life in the universe. So, light. A lot more there than you thought, right?